Hi and welcome to the second part of the thermodynamics set. So in this I'll show you how to do the solution calculations and then we'll move on to looking at entropy and Gibbs energy. So the cycle is more or less just a smaller version of the Born-Haber cycle what you've been doing. So I'll talk you through the steps, then we'll plug in some numbers and it shouldn't be too much of a hassle actually doing these, generally a few easy marks. So we can see here it is our lattice enthalpy of dissociation. It is going to be a positive number because what you are doing is you are taking your ionic solid and you are smashing it up. So you are going back to your gaseous ion. So obviously it's negative. When the oppositely charged ions, the electrostatic attraction pulls them together and bonds form. To go the other way, I want to smash it up, so I've got to break bonds. So I've got to supply energy. So if you are given a negative number in an exam, remember that is probably the formation. Well, it is the formation. You need to use the dissociation, so flip the sign on it. So up here, obviously, we've got our negative and positively charged ions now. Now you do need to know the definitions here for hydration and solution. I'll get them to flash up on the screen now. So make sure you learn them for the exams and obviously understand what they are and what they apply to on this. So the solution is what we want to work out. It's getting from the ionic solid to the actual dissolved ions. So the ions are far apart, fully surrounded by water, and they are not interacting with each other anymore. Now the hydration is the value for when water is attracted to these ions. So I'll go through what can affect that in a second. So up here we've got our gaseous ions, so obviously we need to get water to surround them, get attracted to them. Now water being polar, obviously you've got the delta negative sign on oxygen, you've got the delta positive sign on hydrogen, so it'll depend on the actual charge of these species for which bit of the water actually gets attracted to them. Now you will see it's negative because obviously they are attracted. They are going to form bonds, and forming bonds releases the energy here. So the enthalpy of hydration, you can see I've went from the calcium ion in the gaseous form to the aqueous across here. So water has surrounded that. So it's going to be the delta negative part, it's going to be the oxygen atom which surrounds the calcium. Now the fluoride here, obviously gone to the aqueous form there, so it's going to be the delta positive hydrogen bit which would surround the fluoride. Now for what affects these values, it's quite similar to when you looked at the lattice enthalpy of formation. It's going to be more exothermic if your ion is smaller and has a higher charge. Because if say I had magnesium rather than calcium, the magnesium would have a 2+ charge in a smaller area. So the delta negative signs on the oxygens, they would be more attracted to that magnesium. So similar things, talk about size, charge density and overall attraction, and that is what varies these. Now hopefully you can see I've laid the equation out here for how you actually work it out. Very easy. Enthalpy of solution equals your lattice enthalpy of dissociation plus your hydration values. So this value here, effectively Hess's law, it's all applying it again, that equals the root going round there. Now look at this across here. Remember I've done 2 times minus 506 because I'm doing 2 hydrations. I'm hydrating one fluoride ion and then I'm hydrating the second fluoride ion. So that's why it's 2 times minus 506. So mathematically, if you punch them into a calculator, it's going to be, and obviously add minus 1650 or just take it away, however you wish to type it. And then add 2 times minus 506. And I punched that in beforehand, and that comes out as minus 51 kilojoules per mole. So these were all kilojoules per mole values. So as you can see, this one is exothermic. It does not have to be. You can have ones where your enthalpy of solution comes out positive, so do not worry if you're practicing a past paper question and you see that. So that's enthalpy of solution, fairly easy. Cycle there, and just similar to the lattice enthalpy of formation, talking about charge density for the attraction. Okay, so I will go on to entropy now. Right, so entropy in simple terms, it's usually just described as an increase in disorder or an increase in chaos. Now obviously they're a bit vague words. You will get away at A level just saying an increase in disorder, but strictly what it is, it's a dispersion of energy. So that's why it sort of refers to gas molecules and the actual spreading out of the energy within them. Now there are a few factors which affect it, because temperature, number of particles, mixing of particles. Entropy refers to the number of ways things can be arranged. Now why temperature affects it? Well, temperature will change the physical state. So going from a solid, heating it up, you can get to a gas. Now obviously gases, moving apart, they get dispersed, they are spread out, as opposed to an ordered solid. In a solid, there's only a certain amount of ways you can actually arrange things, whereas in a gas, when they spread out and fill all the available space, you can have them arranged in many different ways. Number of particles, for obvious reasons. If I just have 2 pens, there's only a certain amount of ways that I can arrange these, whereas if I have 20 pens, then I can arrange them in far more different combinations. Now the mixing of particles in a similar manner, I will try and sort of get a little clip of what happens when you add some milk into tea. Should appear about now. Okay, so this is a quick experiment to show how entropy is at work in the mixing of coffee and milk here. So as you can see there, we've got the coffee sitting in, and if I add some milk now, then you can effectively see entropy at work in that it's almost evenly distributed, so it's spread out. Now there is nothing sort of against the rules to say that all of the milk could have just sat in a corner over here and all of the coffee in this region. It's just that entropy talks about probability. So probability wise, for the milk to all sit there and the coffee to sit over here is such an extremely low probability compared to if I look at a chunk here and some of it's coffee and some of it's milk, and ditto if I look at a chunk here and some of it's coffee and some of it's milk. The probability for that is far, far greater than all of the milk to be in one region. So it's such a great probability, in fact, compared to the other. If you were to sit and wait for all of the milk to just randomly gather here, then you would be, well, the universe would end basically. So as you can see there, effectively when you add the particles, they mix and increase the entropy. The reason why with that you imagine them being as two separate entities like this. So I've got the tea there and I've got the milk there. Now at the moment they've got quite low entropy, they are rather ordered. When I mix them together, however, then I can arrange the red and the black in lots of different ways together. I can have them all mixed up, and that increases entropy. So it's the reason why when you mix them together, you don't just end up with the milk on the top and the tea on the bottom, or the other way. It will tend to go where they fully mix and increase entropy, because entropy always looks to try and increase. Now, as we can see up here, this is the general arrangement which you should be able to spot in terms of helping you predict if a reaction has a positive or negative entropy. So solids have quite low entropy, they are nice and ordered. When you heat something up and it turns into a liquid, well, it tends to get a bit more jumbled up. and disorder increases. Aqueous, likewise, that sort of relies more upon this. If you've got different things moving about in there, then it will increase the entropy. And obviously gases, well, entropy wise, they are much bigger than all the others, so it's why things will tend to go towards being gaseous. Now, for how you actually work them out, the entropy change is what you will be looking to work out. So it's the sum of the entropies of the product, so the sum there, minus the sum of the entropies of the reactants. Now remember to take into account coefficients. So if you've got 2 of carbon dioxides, then you need to do 2 times the entropy of carbon dioxide. Now the unit for entropy, joules per Kelvin per mole. So be very careful when we come on to doing the Gibbs calculations in a bit. If you've been given enthalpy change in kilojoules per mole, then either you need to multiply that by 1,000 or you need to divide your entropy change by 1,000 so that the units can cancel each other out. So they need to be in a similar unit. Now I'll do a couple of examples of looking at entropy, seeing if we can work out if it's positive or negative. So I'll just pause here. Okay, so I've got a few examples of equations on the board here, and we'll try and figure out if entropy is increasing or decreasing for them. So the top one, as we can see up here, we are starting with hydrochloric acid, which is aqueous. We are chucking in some solid sodium carbonate. Now what we are getting out, carbon dioxide, because obviously we acid plus carbonate, the salt there, sodium chloride, and some water. Now entropy in this case would be positive. Easy way to spot why. No gases on this side, gases there. Gases have a massive entropy compared to the others. So the entropy change here would be positive. So entropy favours this reaction. Now second reaction, so we've got oxygen as a gas reacting with iron, so just an oxidation, reduction, and we are getting the iron oxide produced over here. Now you will see on this case we've got the gas across here plus a solid, and it leaves us with just a solid. So that's not favourable for entropy because we're getting rid of disorder here. We're removing the highly disordered gas and making a fairly ordered solid. So entropy here, the change would be negative. Now this equation would be pretty hard to tell without numbers. The reason why, you were effectively starting with 2 gaseous molecules and finishing with 2 gaseous molecules. So give or take, it's going to be pretty close, around 0 for this. They're all fairly simple, so it would be quite hard to tell. Just delta S is about 0. So a little bit of a trick question there. Now you can go against entropy because obviously some reactions occur which go against entropy. Life is an example of that. I'm not going to go to all the ins and outs of it, but the reason why you've got complex life forms, some more complex than others, which is why you're studying chemistry rather than film studies, is work can be put in to go against entropy. So an easy example for that is a student's notes will become highly disordered over time. If they're just left, they start off nice and neat at the start of the year, they become disordered. I have to now put in work and go around, slap said student across the back of the head, and they put in work with muscles and ordering, and effectively that is entropy, well, going against entropy as such. It's making the notes more ordered, but you're actually performing work with the muscles, and the overall entropy in the universe would increase because of that. So the universe is always looking to increase in entropy. So I've got 2 pictures here to show this. If you look at these, nice pretty things. So what we see there is the universe at the start, so a nice evenly distributed hot plasma, and effectively it's become a mess thereafter. Everything's spreading out, and the reason you've got sort of galaxies and clusters and all that forming is gravity, but gravity will be overcome by entropy in the end. Effectively, everything will just spread out so much, it'll be a nice, cold, desolate place, and it's called the heat death of the universe. One of the ways that things could end. But don't worry about that, because if you fail, you'll be dead long before that happens. Right, so that's sort of all the ins and outs, the theories of what entropy is. Now, the two main things is obviously we're going to do a calculation working out entropy change, and then we are going to look at the Gibbs energy, so doing the calculations involving that. So I'll stick some numbers up on the board now. Okay, so numbers wise, and just before I start, thank you to one of my students who donated those pictures. If you are interested in anything astronomy wise, I've put her blog in the link below. Feel free to go and check it out and learn something interesting. So for all you budding astronomers out there, go and geek it out. Right, so we've been given some enthalpies of formation here, we've been given some entropies of compounds, and we will say we're going to work out Gibbs energy at say 450 Kelvin. So how to do that? Well, the equation, what you need to know is this. So as you can see, this is Gibbs energy. It links together enthalpy change and temperature and entropy there as well. So you should be able to spot if enthalpy is always negative and entropy is always positive, then Gibbs will always be negative. So a negative number for this means the reaction is feasible, it will go. If this comes out positive, it will not. Simple as that. So 0 is the cut-off point where something is in equilibrium, it's kind of just about possible. But we'll come on to doing one of those in a second. So I need to work out my enthalpy change. So I've been given my formation values across here. So I'll just do a Hess's cycle. So this links back to when you did them in Chem 2. So if you've forgotten how to do them, go back and practice. So we've got our elements down the bottom. I'm not going to bother balancing it. The reason why, it doesn't really matter, because we are looking at formation, how many moles are formed. I know this equation's balanced. So my elements there, put in the numbers on the correct arrows. So obviously carbon 0, because it is just an element in its standard state under the standard conditions. So there's the numbers. So if I want to find out the enthalpy change here, all I'm going to do is minus 110.5, take away minus 271.9. So that comes out as 161.4. So there's my enthalpy change. Now my entropy change, how to work out that? Well, entropy change equals the sum of the product minus the sum of the reactants. So all I would need to do is I'm going to have my products, so my carbon monoxide and iron, if I add these two together, and then I will subtract the entropies of these. So I will subtract 58.5 and I will subtract 5.7. And that comes out as 160.7. Now again, remember units, I've shown you there, entropies in joules, enthalpies in kilojoules. So I should divide this by 1000 so that the units are comparable. Now, say if I want to work out if a reaction is feasible at a certain temperature, say 450 Kelvin, then what I would do So there, my enthalpy change minus, and then the temperature which you are looking at, so 450 Kelvin. You must use the Kelvin scale for this, by the way, because the Kelvin will effectively cancel out the Kelvin unit up here. And times by the entropy change. Obviously I've divided by 1,000 to keep them in the similar units. And since I'm using kilojoules per mole, then this will give me a delta G value in kilojoules per mole. So that comes out as plus 89. 89.085 if you want a few more significant figures in there. So with that being positive, that tells me at this temperature that this reaction is not feasible. Now that should make sense because this is effectively an extraction of metal. We are starting with the ore across here and getting the pure metal across there. Now extractions of metals are done at very high temperatures. So you've done them in sort of, again, back in Chem 2, it's going to probably be several hundred higher than that. Now, if I want to work out at what temperature the reaction does become feasible, remember the maximum value what delta G can have is 0. Because a negative value will go, a positive will not. 0 is that break point. So what you would do, you would rearrange this equation to make delta G equal 0. Apologies if this is your glove left in the room. Now if I rearrange this equation to make T the subject, then I've got that equation. So all I would do is my enthalpy change put in there, my entropy change here, remember kilojoules, so the 160.7 divided by 1,000 underneath. If you plug that in and work out temperature, that comes out as 1,004 Kelvin. So I must have the temperature to a minimum of that amount, and then the reaction will proceed. Higher is better. Higher will make it go even more. So those are the two main types of calculations which you will look at. Either A, working out Gibbs energy, or B, working out a temperature at which a reaction becomes feasible. So that is it for the entire thermodynamics topic. So if you've liked the videos, I've been asked to give a shout out. If you could post a comment below saying, "Hi Becky," that would be appreciated. Thank you.